put your headphones on. You press play, the bass hits. Your ears feel it, your chest almost feels it, and somewhere deep in the cup of that driver, sitting millimeters from your eardrum, something is happening that nobody at the headphone store ever told you about. We are not talking about magnets and cones and wires. We are talking about something older, stranger, and sitting right at the edge of the most counterintuitive physics ever discovered. Quantum mechanics is not just for particle accelerators and cold laboratories. It is in the thing on your head right now. And the story of how it got there starts not with a tech company, not with a music producer, but in 1874 in Germany with a man who had absolutely no idea what he was beginning. Here's the thing, the word quantum gets thrown around a lot these days. Quantum this, quantum that, quantum mattresses, quantum coffee. Most of it is nonsense, but in the specific case of sound, of vibration, of the very molecular machinery that turns electricity into the thump you feel in your ears, quantum mechanics is not a marketing word. It is the actual documented, peer-reviewed description of what is physically happening. And the bridge between the headphones on your head and the deepest rules of the universe is a particle so small it barely registers as real, and yet it carries every note you have ever heard. Its name is the phonon. If you value documented physics history and real science like this, subscribe right now. It is the best way to support this channel. Also, drop a comment telling us what city you are listening from. This script is researched and sourced from peer-reviewed physics literature, including the Phonon entry in the Physical Review Letters Journal and MIT's Open Physics course notes from Gang Chen, Soderbergh Professor of Power Engineering at MIT, published and verified as of 2010 and updated in ongoing research, as well as Cornell University research published in PRX Quantum in August 2024. These are not blog posts. These are the primary sources. Back to the story. 1874, Berlin. Ernst Werner von Siemens is 57 years old and already one of the most powerful engineers in Europe. He has built telegraphs, undersea cables, electric railways. On August 25th, 1874, he files German patent number 96. The device he describes is a circular coil of wire positioned inside a magnetic field, supported so it can move axially back and forth. He calls it a magneto-electric apparatus for obtaining mechanical movement from electrical currents. He does not call it a speaker. He does not use it to play music. He has no way to amplify sound yet. But the physics he patents that day will, within 50 years, sit inside every radio, every phonograph, every pair of headphones ever manufactured. What Siemens has stumbled into is the Lorentz force. The principle, named after Dutch physicist Hendrik Lorentz, states that any wire carrying an electrical current inside a magnetic field experiences a force. The direction of that force is perpendicular to both the current direction and the field direction. In plain terms, push electricity one way through a wire, and the wire moves sideways. Reverse the electricity, and the wire moves the other way. Do that thousands of times per second in a pattern that matches a sound wave, and whatever is attached to that wire will vibrate in exactly the same pattern. Attach a thin cone of paper or plastic to that wire, and those vibrations compress and decompress the air in front of it. That moving air reaches your eardrum. You call it music. Alexander Graham Bell files a patent for the telephone in 1876. 2 years later, Siemens applies for a second German patent, number 2355, for a non-magnetic parchment diaphragm as a sound radiator for his moving coil device. The diaphragm, he suggests, could take the form of a cone. That is the first recorded patent for a speaker horn. The world's first patent for the actual speaker cone shape is a footnote in most engineering history, and that footnote belongs to the same man who invented the electric railway. The machine sits dormant for decades. Nobody can amplify the electrical signal enough to make it useful. Then comes the vacuum tube, then radio, then Chester W. Rice of General Electric and Edward W. Kellogg of AT&T co-patent the modern moving coil speaker in 1924. Their device, the radiola loudspeaker number 104, produces the first clean, boosted, frequency-balanced audio that a mass consumer can actually use at home. 1925, they install it in talking pictures. 1926, the Vitaphone system, powered by Western Electric's 555W driver, brings synchronized sound to cinema for the first time. The driver has a frequency response of 100 to 5,000 Hz and an efficiency of 25%, compared to about 1% efficiency in modern drivers, because back then the amplifiers could only push 10 watts. 1% efficiency sounds bad, but the math behind the driver, the Lorentz math, the push-pull of current and magnetic field, that part has not changed. Every pair of headphones you have ever owned works on the same physical principle Ernst Werner von Siemens sketched in Berlin in 1874. A wire coil, a magnet, a cone, current flows, force appears, air moves. You hear? Here's where it gets strange. The cone in your headphones is not moving one single object as a whole, like a piston. It is made of billions and billions of atoms. Paper, plastic, aluminum, or a composite blend, all of them attached to each other by chemical bonds. When the voice coil pushes the base of that cone, it does not push all the atoms at once simultaneously. It pushes the atoms at the base, and those atoms push their neighbors, and those neighbors push their neighbors, in a wave that propagates through the material. That wave has a speed determined by the stiffness of the material and the mass of the atoms. In paper, that propagation speed is roughly 3,500 meters per second. In aluminum, it's over 5,000 meters per second. The wave rips through this material in microseconds, and the whole cone vibrates as a unit only because that propagation is so fast relative to the audio frequencies you're playing. But here's what that wave actually is, at the atomic level. And this is the part nobody at a consumer electronics store will ever explain to you. Every atom in that cone is bonded to its neighbors. Those bonds behave exactly like tiny springs. Pull two bonded atoms apart, and the bond pulls them back together. Push them together, and the bond pushes them apart. This is Hooke's law at the molecular level. Now, in classical physics, you might think these spring-like bonds can store any amount of energy, any amplitude, any frequency, continuous. That is the classical picture. That is wrong. In 1900, Max Planck was trying to solve a different problem entirely, the so-called ultraviolet catastrophe, which was the classical physics prediction that a hot object should radiate infinite energy at short wavelengths. He found the only mathematical fix was to assume that energy comes in discrete chunks. 1 chunk, 2 chunks, 3 chunks, never 1.5 chunks. The size of each chunk depends on the frequency, and the proportionality constant is today called Planck's constant, written as h, a number approximately 6.63 times 10 to the negative 34 joule seconds. Tiny, absurdly tiny, but non-zero. Albert Einstein took Planck's idea and in 1905 applied it to light. Light is not a continuous wave, he argued. Light is made of discrete particles, each carrying 1 chunk of energy. Those particles are photons. The scientific community largely hated this idea for a decade. Then Einstein was proven right. The physicist Yakov Frenkel, working in Leningrad in the early 1930s, took the same logic and applied it not to light, but to sound in a solid. If light comes in chunks called photons, then vibrational energy in a crystal lattice also comes in chunks. He named those chunks phonons, from the Greek word phone, meaning voice or sound, deliberately echoing the word photon. The name was not just poetic, the analogy was mathematical. A phonon is the smallest possible unit of vibrational energy at a given frequency in a solid. You cannot have half a phonon. You cannot have 1.7 phonons. You get 0 phonons, 1 phonon, 2 phonons, 3. Integer steps, quantized, quantum, cold, discrete, indivisible. MIT's Gang Chen, the Soderbergh professor of power engineering, puts it cleanly in his course materials. Low frequency vibrations in atoms correspond to sound, while higher frequencies correspond to heat. At each frequency, the vibrational energy must be a multiple of a basic quantum of energy proportional to the frequency. The basic quantum is 1 phonon. Push a loudspeaker cone gently and you're sending a flood of phonons through its material. Turn the volume up and you send more phonons. Turn it down and you send fewer. The quietest sound theoretically possible at any given frequency consists of a single phonon. 1. Indivisible. Quantum. Now think about bass. Bass frequencies are low. 20 Hz, 40 Hz, 80 Hz. A phonon at 20 Hz carries an almost incomprehensibly tiny amount of energy. We are talking about energy on the order of Planck's constant multiplied by the frequency, which at 20 Hz is approximately 1.3 times 10 to the negative 32 joules. That is so small that the thermal energy of atoms at room temperature is roughly 1 billion times larger. This means, at normal temperatures and normal sound levels, your headphone cone is flooded with trillions and trillions of phonons. The quantum discreteness is invisible at human scales. The bass does not feel choppy or quantized because each discrete step is so small that no human ear, no instrument of the 1980s could ever detect it, but researchers can. In June 2023, a team led by engineering physicist Andrew Cleland at the University of Chicago published a paper in the journal Science demonstrating that they had successfully split a single phonon using an acoustic beam splitter. When they sent a single phonon toward the splitter, it did not go one way or the other. It went both ways simultaneously, existing in a quantum superposition. Then it interfered with itself, exactly as quantum particles do, changing where it ultimately ended up. Cleland told Science News, "What's really kind of amazing about that is that these sound waves carry a very, very small amount of energy, because it is a single quantum." The experiment was conducted with sound frequencies millions of times higher than human hearing, and the device had to be cooled to temperatures close to absolute zero to eliminate the background noise of thermal phonons. But it proved beyond question that phonons are real quantum particles, and that they exhibit the full weirdness of quantum mechanics, superposition, interference, and indivisibility. Sound, quantum, weird. The physics behind why this connects to your bass specifically involves the quantum harmonic oscillator, which is one of the most important models in all of physics. Consider any two atoms bonded together. They are not sitting still. Even at absolute zero, according to quantum mechanics, they are vibrating. This is not just theoretical uncertainty. It is a real, measurable, non-removable energy called zero-point energy. For a quantum harmonic oscillator, the ground state energy is 1/2 times Planck's reduced constant times the angular frequency of oscillation. The oscillator can never be at complete rest. This was demonstrated mathematically by Heisenberg's uncertainty principle. If you knew exactly where the atom was and that it had exactly zero momentum, you would violate the principle. Nature does not allow it. In 1935, physicist R.A. Newing published a paper in Nature, volume 136, showing that this zero-point energy can be directly derived from the uncertainty principle using only the relationship between position, momentum, and energy in a simple harmonic field. Zero-point energy is not an artifact or a rounding error. It is built into the mathematics of atoms themselves. What this means for sound is profound. In the diaphragm of your headphone, in the metal or paper or polymer of that cone, every single chemical bond is a quantum harmonic oscillator. Every bond vibrates at its own natural frequency. The stiffness of the bond determines the frequency, and the frequency determines the phonon size, and the phonon size determines how that bond responds to external vibration. When the voice coil pushes the diaphragm at, say, 60 Hz, that 60 Hz signal propagates through the material as a wave of phonons. But different frequencies can interact. MIT's Gang Chen notes that unlike photons, which generally do not interact with each other if they have different wavelengths, phonons of different wavelengths can bump into each other and mix, producing new wavelengths. This is called phonon-phonon scattering, and it is a quantum mechanical phenomenon with no classical equivalent. It is the reason designing headphone materials is so hard. The phonon interactions inside the diaphragm material determine how faithfully the cone vibrates at each frequency. Get the material wrong and phonon scattering smears out the bass response. Get it right and the phonon pathways align. The wave propagates cleanly and the bass hits the way the engineer intended. Tight, clean, quantum. The University of Vermont Physics Department published research in August 2025 in a paper reported by Science Daily, in which Professor Dennis Cluggerty and student Nam Din solved a 90-year-old puzzle in quantum mechanics. They created a fully quantum mechanical model of the damped harmonic oscillator, the mathematical system describing exactly how atoms in a solid vibrate and lose energy to their surroundings. The original classical model was built by British physicist Horace Lamb in 1900, before Werner Heisenberg was even born. Lamb showed how a vibrating particle in a solid loses energy to elastic waves, the very same phonons we are discussing, that feed back on the particle and cause it to slow down. For 90 years, nobody could produce a complete quantum version of Lamb's model that preserved the Heisenberg uncertainty principle. Cluggerty and Din did it in 2025, using a mathematical technique called a multimode Bogoliubov transformation. What this means in practice is that physicists now have a rigorous quantum framework for predicting how atomic vibrations decay in materials, how phonons die out, which in turn will guide the design of future audio materials where phonon pathways can be deliberately engineered. And now we are coming back to your headphones. Because the story does not stop in the 1970s. It is happening right now. Professor Robert J. Wood at Harvard University's John A. Paulson School of Engineering and Applied Sciences, holder of the Harry Lewis and Marlon McGrath Chair, leads a team working on the next generation of headphone drivers. Their finding, posted publicly through Harvard's Office of Technology Development in late 2025, states plainly, existing electromagnetic drivers have already been optimized to their physical limits. The classical Lorentz force design that Siemens invented in 1874, which Rice and Kellogg commercialized in 1924, has been pushed to its ceiling. The next step is drivers based on dielectric elastomer actuators. These are soft polymer films that change shape when voltage is applied. They operate on electrostatic attraction rather than magnetic force, and their mechanical behavior at the atomic level is governed by different phonon interaction pathways than traditional metal or paper cones. Wood's team is seeking commercialization partners to build proof-of-concept devices. The promise is significantly improved bass response, more compact assemblies, and better noise cancellation, all arising from different materials with different quantum vibrational properties. In other words, the bass engineers of the future are quantum engineers. The quantum nature of sound also sits beneath something called the Brillouin zone. When physicists map out which phonon frequencies can actually exist in a given material, they map them in something called a dispersion relation, a curve that shows frequency on one axis and wave vector on the other. This dispersion relation has a hard cutoff determined by the minimum possible wavelength in the material, which is twice the spacing between atoms. No phonon with a shorter wavelength can exist in that material. This is a quantum constraint with no classical analog. For typical solid materials, that atomic spacing is around 1 to 3 angstroms, meaning the maximum phonon frequency sits in the terahertz range. Base frequencies at 20 to 200 Hz are far below this limit, which means base phonons are long wavelength acoustic phonons, the most classical behaving members of the phonon family. They propagate almost like classical sound waves, but they are still quantum. They still come in integer counts, and their interaction with higher frequency phonons in the same material, those scattering events, still obey quantum rules. Here's another layer. When you crank up the bass on your equalizer, you're not simply pushing more energy through a wire. You are changing the number of phonons being injected into the diaphragm material per second. Increase the current in the voice coil, and you increase the Lorentz force. Increase the Lorentz force, and more phonons get launched from the point of contact between the voice coil former and the base of the cone. Those phonons propagate outward through the material. The cone bends and flexes. Some phonons reach the outer edge and couple to the air in front of the driver. Others scatter internally, get absorbed by the material, and turn into heat. The efficiency number from Chester Rice and Edward Kellogg, 1% in modern drivers, is a direct measurement of what fraction of those phonons actually make it to the air, as useful sound versus being lost to internal phonon scattering and dissipation. 1%, 1%. 99 phonon seconds of energy go in. One comes out as bass. The heat you feel when you touch speakers that have been running loud for an hour, that is the phonons that did not make it. Quantum energy that scattered off defects, grain boundaries, and impurities in the cone material and turned into heat phonons, which are higher frequency vibrations that we do not hear, we just feel as warmth. This brings us to the most recent frontier. In January 2024, researchers from the Stiller Research Group, led by Dr. Birgit Stiller at the Max Planck Institute for the Science of Light in Germany, published findings in Physical Review Letters. They managed to cool a sound wave propagating through a 50 centimeter glass optical fiber by 219 degrees Kelvin, from room temperature down to 74 Kelvin, which is negative 194 degrees Celsius. They did this using laser light and the nonlinear optical effect called stimulated Brillouin scattering, in which light waves couple directly to sound waves and can transfer energy in either direction. By shining the right frequency of laser light, they extracted thermal phonons from the fiber, reducing the phonon population by 75% and dramatically reducing acoustic noise. Dr. Stiller noted that this opens the door to a new landscape of experiments that will give deeper insights into the fundamental nature of matter. That fiber is 50 centimeters long. It is not a microscopic chip in a cryogenic laboratory. It is close to the length of a forearm. The fact that researchers can cool the phonons in an object that large pushes the boundary between classical acoustics and quantum acoustics much closer to the scales that real engineering deals with. The Cornell University study, published in PRX Quantum in August 2024, from the lab of Professor Gregory Fuchs in the Department of Applied and Engineering Physics, demonstrated something else entirely. They built a microscopic speaker on the surface of a diamond chip, operating at a frequency exactly matching an electronic quantum transition in the diamond's nitrogen vacancy centers. The acoustic waves drove quantum jumps between electron orbital states, meaning mechanical vibration, literal sound, was used to control single electrons at the quantum level. Postdoctoral researcher Brendan McCullion described it directly. The acoustic waves excited the electrons through a mechanism similar to pumping a playground swing. When the vibrations are in sync with the electron motion, they transfer energy. The speaker on a diamond chip was controlling single electrons. Sound was controlling quantum bits. Audio engineering and quantum computing were, for a moment in August 2024, the same thing. That is not metaphor. That is a published paper. Now, let us bring this all the way home to the inside of your headphone cup, because there is one more piece that connects everything. When the acoustic phonons launched by your voice coil reach the boundary between the solid cone and the air in front of it, something happens that physicists discovered has a quantum mechanical flavor. A team at the Massachusetts Institute of Technology confirmed in work by Chen's group, published and verified in ongoing materials research, that when phonons hit an interface between two materials, they can bounce like particles off a wall. Not smoothly, not continuously. They bounce, they scatter, they partially transmit and partially reflect, following probabilistic quantum rules. The fraction that make it through the interface determines how efficiently the driver couples to the air. This coupling efficiency is one of the key parameters in speaker design, and it is rooted in phonon quantum mechanics. When audio engineers measure a speaker's dispersion and frequency response curves in an anechoic chamber, they are, at the quantum level, measuring phonon transmission probabilities across material interfaces. 40 years from now, if Wood's team at Harvard succeeds, or if another materials team designs a dielectric elastomer driver tuned at the phonon level for maximum low-frequency transmission, the bass you feel will be designed phonon by phonon, not as a metaphor. literally at the level of which quantum vibrational modes the material supports, which phonon pathways the material suppresses, and which ones it amplifies. The equalizer slider labeled base will be, in the most fundamental physical sense, a phonon population controller. But here's where we arrive. Here's the cold moment. In 1874, Ernst Werner von Siemens received German patent 96 for a coil that moves in a magnetic field. He did not know about phonons. He did not know about Planck's constant, published 26 years later. He did not know about zero-point energy, formalized in the 1920s and 30s. He did not know about phonon-phonon scattering, or Brillouin zones, or quantum acoustic beam splitters, or diamond chips with microscopic speakers controlling single electrons. He knew the Lorentz force. He knew wire, current, and magnets. And in Berlin, in 1874, with those three things, he built the machine that the entire phonon conversation sits inside. Every note you have ever heard through a speaker or a pair of headphones has traveled from electricity to Lorentz force, to cone vibration, to phonons, to air pressure, to your eardrum. The quantum step in that chain has been real and active since the first one played. Nobody told you because nobody knew it was happening. The engineers who built the equipment in the 1920s did not know about phonons. The engineers who tuned the drivers in the 1960s and 1970s did not know they were engineering phonon transmission coefficients. They knew empirically which materials worked, which cone shapes were better, which magnet sizes produced better bass. The quantum mechanics was always underneath, governing everything, invisible. The phonon was named in the 1930s. Its particle nature was proven in the 2020s. The theory needed to describe how phonons damp inside a vibrating solid was completed in 2025. The device that uses quantum acoustic principles to control electrons was demonstrated in 2024. And the headphone that you will buy 10 years from now will be designed using all of it. In the archives of the German Patent Office, patent number 96 from August 25th, 1874, describes a device for obtaining mechanical movement from electrical currents. At the bottom of that mechanical movement, at the absolute floor of what is physically happening in the material, are particles that Max Planck had not yet imagined, that Heisenberg had not yet constrained, that Yakov Frenkel had not yet named, indivisible, quantized, real, the bass hits. The phonons move. They always did. Let's go deeper on the material science because the physics of bass is inseparable from the physics of the thing that carries it. Paper has been used in speaker cones since Rice and Kellogg built their first prototype in 1921 at Schenectady, New York. It is still used today. Why? Because paper is light and it is well damped. The cellulose fibers in paper cone material have a disordered structure. There are no clean crystalline planes for phonons to travel along. The result is that high-frequency phonons scatter heavily in paper, which means paper does not ring and resonate at high frequencies the way a metal cone might. This is a phonon effect. Paper kills unwanted high-frequency vibrations faster than metal because its disordered atomic structure offers more scattering sites. Metal, by contrast, is crystalline. In aluminum, for example, the atoms sit in a face-centered cubic lattice with a spacing of roughly 2.86 angstroms. Phonons can travel long distances through the lattice before scattering, because the periodic structure provides clean pathways. The result is that aluminum cones propagate vibrations very efficiently, but ring, producing audible resonances at specific frequencies where the phonon wavelengths match the physical dimensions of the cone. The peak energy product of neodymium magnets used in modern drivers reaches up to 500 kilojoules per cubic meter, compared to the Alnico magnets dominant from World War II through the 1960s, which max out at about 80 kilojoules per cubic meter. More magnet energy means stronger magnetic field, means stronger Lorentz force, means more phonons injected into the cone per unit of current. But injecting more phonons into a poorly damped metal cone just means more ringing, more phonon-phonon scattering in the bad direction. This is why the choice of cone material is not just an acoustic engineering problem, it is a quantum materials problem. The engineers who switched from paper to aluminum to composites like Kevlar, Nomex, carbon fiber, and polypropylene in the 1980s and 90s were empirically optimizing phonon propagation paths without knowing it. Carbon fiber cones are stiff and light, with a high Young's modulus, meaning the bonds between atoms are very stiff springs, which means acoustic phonons propagate at very high speeds, reducing time for phonon-phonon scattering during transit. The result is a cone that moves as a rigid piston at low frequencies, exactly what you want for clean bass. But carbon fiber is poorly damped at the microscopic level, similar to metal. So the engineering solution is to laminate it. Carbon fiber skin, polymer foam core, carbon fiber skin again. The foam core introduces a disordered material layer that absorbs high-frequency phonons, while the stiff carbon fiber surfaces propagate the low-frequency bass phonons efficiently. 3 layers, 3 different phonon environments. Engineered, Planck's constant. 17 meters of wire, neodymium magnet. Now we go back into quantum territory, because there is a concept called the acoustic branch of the phonon dispersion relations that explains specifically why bass is different from treble at the quantum level. In any solid material, there are two types of phonons: acoustic phonons and optical phonons. Acoustic phonons are the ones where neighboring atoms move together in the same direction. They are the long wavelength, low frequency phonons. They correspond to sound. Optical phonons are where neighboring atoms move in opposite directions. They are higher frequency and do not propagate as sound waves in the classical sense. Bass frequencies from 20 Hz to roughly 200 Hz are in the extreme low end of the acoustic phonon branch. The wavelength of a 20 Hz acoustic phonon in a typical polymer is roughly 175 millimeters, far larger than the physical dimensions of any headphone driver. This means the phonon at bass frequencies is not bouncing around inside the cone material like a particle. It is a smooth, long, classical-looking wave that the entire cone participates in coherently. This is why bass feels like a push, a pressure, something you sense with your whole ear, rather than a detail you resolve with pitch discrimination. The phonon is so long wavelength that it looks like a classical wave. The quantum nature is hidden. Turn up the treble. A 10,000 Hz acoustic phonon in aluminum has a wavelength of roughly half a millimeter. Now the wavelength is comparable to the physical dimensions of features in the cone. Phonons bounce off edges, holes, structural ribs in the cone. The quantum particle-like nature of phonons starts to matter more. The behavior becomes more complex, more frequency selective, more dependent on specific material geometry. This is why tweeters are small and woofers are large. It is not just that larger cones move more air. It is that at bass frequencies, the phonon wavelengths are large, and you need a large surface to couple efficiently to those long phonons and transmit them into air. At treble frequencies, the phonon wavelengths are short, and a small dome tweeter couples efficiently because its dimensions match the phonon scale. The size is the phonon. Now, in 2016, the Quantum Music Project in Denmark ran an experiment at Aarhus University where physicists, including Klaus Molmer, professor of quantum optics, combined a grand piano with quantum acoustic sounds derived from a Bose-Einstein condensate, a cloud of atoms cooled to near absolute zero where quantum effects dominate. Physicist James Schloss, writing in Aeon in October 2023, described the experience of playing with these quantum tones. The frequencies of vibrations in a Bose-Einstein condensate do not follow the normal musical exponential law, where each octave doubles the frequency. Instead, the quantum atomic interactions change the dispersion relation, shifting the harmonic series in ways that have no equivalent in classical music. When Schloss added harmonic overtones to a waveform built from quantum mechanics, each addition created interference phenomena that have no classical analog. The music was strange. The physics was real. Molmer's hope, stated in the 2016 promotional video, was that musicians, with their strong intuition for waves and wave behavior, might give physicists new insights into quantum mechanics. That exchange, from sound to quantum and back, is exactly what the phonon represents. You use music to feel quantum effects. The quantum effects govern how you hear music. Since 1924, when Rice and Kellogg ran 1 kilowatt of power through the first practical speaker and achieved 1% efficiency, turning electricity into usable sound, engineers have been trying to push that number up. The theoretical limit for a dynamic driver moving air is well understood in terms of classical acoustic physics. The real ceiling is at the phonon boundary, at the quantum mechanical efficiency with which electrical energy becomes phonon energy in the cone, and phonon energy in the cone becomes phonon energy in the air. Modern high-end headphone drivers achieve between roughly 0.1 and 3% efficiency. The rest is heat. Phonons scattered sideways, absorbed by the voice coil former, dissipated in the surround material, lost to the chassis. Every milliwatt of that heat has a quantum name. It is a phonon that did not make it to your ear. The neodymium magnets in premium headphone drivers, introduced broadly in the 1980s as neodymium iron-boron compounds, produce magnetic field strengths at the voice coil gap of roughly 1 to 1.5 Tesla, compared to about 0.8 to 1 Tesla for ferrite magnets. The force factor, called the BL product, which multiplies the magnetic field strength B in Tesla by the length L of wire and meters immersed in the field, reaches values around 4 to 5 Tesla meters in premium driver designs. This force factor directly determines how many phonons get injected into the cone per ampere of current. A higher BL product means stronger phonon injection at every bass beat. Every single beat. When Chester Rice and Edward Kellogg filed patent number 1,715,15,59 in 1924, they did not write the word phonon. The concept did not exist yet. They described the electromagnetic principles, the voice coil, the cone, the suspension, the magnetic field. The quantum machinery underneath their invention was invisible to them. It is still largely invisible to consumers today, but it is the machine that is actually running. When the University of Vermont team published their quantum harmonic oscillator solution in August 2025, and when they noted that their model predicts precisely how the uncertainty in the position of a vibrating atom changes with its interactions with neighboring atoms, they were solving the mathematics of every single atom in every single speaker cone ever built. 151 years after Siemens filed patent 96 in Berlin, the quantum foundation of his machine was finally fully written down. And there is this. In the Science News report from June 2023 about Andrew Cleland's team at the University of Chicago splitting single phonons with an acoustic beam splitter cooled to temperatures close to absolute zero, physicist Andrew Armour of the University of Nottingham offered a comment on where phonon quantum research is going. He said that what Cleland's team was doing is extending the quantum toolbox, that people will build on it, and there's no sign of it stopping anytime soon. Armour was not talking about headphones. He was talking about quantum computers and ultra-sensitive measuring devices. But the phonon he was describing, the indivisible quantum particle of sound, is the same phonon moving through the paper or metal or polymer in the driver cup on your head right now. The only difference is scale and temperature. At room temperature, at the frequencies you call base, the quantum discreteness is washed out by the thermal storm of trillions of phonons. But the rules are the same. The phonon is the same. The Planck constant governs both. The phonon on the diamond chip at negative 200 degrees Celsius, controlled by a laser with precision to a single quantum, and the phonon cascading through a 50 millimeter neodymium driver at room temperature because you pressed play. Different scales, same law. Now, there is one final fact that sits underneath all of this, something found not in a technology report or a physics paper about audio, but in a physics paper from Nature, volume 136, 1935, by R.A. Newing, titled Uncertainty Principle and the Zero-Point Energy of the Harmonic Oscillator. In that paper, Newing proved that the zero-point energy, the irreducible minimum energy of a vibrating system, can be derived purely from the uncertainty principle. The oscillator vibrates because it must, not because we push it, not because energy was supplied, because knowing perfectly where an atom is and knowing it has zero momentum simultaneously is physically impossible. The universe refuses to allow it, so the atom moves, always, even at absolute zero. The bonds in your headphone cone are vibrating right now, even in the silence between songs, even with no current flowing, even with no music playing. The lowest possible energy state of the system is not silence. There is no silence at the quantum level. There is only a minimum hum, 1/2 times Planck's reduced constant times the natural frequency of each bond, summed across every atom in every bond in the entire structure, adding up to a number that is too small to hear, too small to measure with any microphone, but real and non-zero, and guaranteed by Heisenberg's uncertainty principle, which Werner Heisenberg published in 1927, 53 years after Ernst Werner von Siemens filed patent 96 in Berlin. You put your headphones on, the bass hits, and underneath that hit, underneath the Lorentz force and the paper cone and the neodymium magnet and the voice coil wound from 17 meters of copper wire, underneath all of it, in the lattice of every material in the driver, the atoms are already moving. They were always already moving. The universe does not come with a mute button.